Welcome to a presentation on Project SPUD, a single core processing unit and display. This is our team for Senior Design 2, Fall Semester 2025. From left to right, we have Muhammad, the hardware design, Frank, the lead, Gabriel, the electrical design, and Valentina, the SoC and RTL design. What is Project SPUD? A custom RISC-V CPU implemented onto an FPGA with an LED display for visual feedback. Modern processors are fully optimized and difficult to inspect, so SPUD proposes a custom, modifiable, demonstrable, and accessible CPU for educational and entertainment purposes. C programs can be directly run on the FPGA-based CPU. CPU and system on a chip are also implemented into the Verilog. A custom display core drives the 64 by 64 RGB matrix, and an arcade controller will be the main interface to control our interactable demos.
Our motivation for this project was to take advantage of the fact that we are all computer engineering majors. We wanted to understand the fundamentals of computer architecture, RTL design, and programming languages so that we could build something that challenges us in a new and creative space. We wanted to develop certain skills that will prepare us once we graduate in our desired careers, earn the title of computer engineer, and most importantly, we wanted to have fun.
First, we wanted to design our own embedded processor that was specifically tailored for our project, instead of relying on an off-the-shelf core. To make the system useful, we developed a C library that gives us control over peripherals like UART, the display, and GPIO pins. On top of that, we added custom registers inside the SoC, so we could directly control hardware through our own instructions. We also worked on configuring the RV32IM toolchain. This allows us to take C code, generate instructions, and load them directly into RAM to run on our processor. Finally, one of our big objectives was to have each team member create their own interactive demo program. That way we could all test and show off different capabilities of the CPU.
Our spud CPU has the following specifications. It has a CPU frequency that can go up to 100 megahertz using overclocking, and also a processor performance that goes up to 10 MIPS, which means that we can run many operations within a decent amount of time. Our LED matrix has a refresh rate of up to 500 Hz, which is a sweet spot for LED matrices, and our CPU can run operations like arithmetic operations, jump, and memory operations. We chose the Adafruit 64 by 64 RGB LED matrix out of all the other LED matrix models due to the fact that it fit our size requirement and it was from a reputable company that we could trust. As for the reason why we chose a matrix display over other display types is because they're very bright, which allows us to demonstrate them in all possible locations without having to worry about light pollution, and they work very well with FPGAs due to the fact that they work best with high data rates and parallel operations, which is something FPGAs excel at. Other display types may have saved us some power, but ultimately we decided to choose the matrix display for the brightness and for the low level look that it has, which fits our project perfectly.
For our FPGA selection, we compared 3 different boards: the Xilinx RD-S7, the Xilinx RD-A7, and the Intel Cyclone 5 starter kit. The RTX-7 board has more logic cells and flip-flops, which makes it really powerful, but it also is the most expensive board. The Cyclone 5 offers strong communication protocol support, but it uses Quartus Prime, which we're not as familiar with as we are with Vivado. The RD-S7 is smaller than the 2 other boards, but it provides just enough logic cells, block RAM, and memory for our SoC, and just aligns well with our goals. So ultimately we chose the S7 because it gives us the right balance of cost and ease of development.
For our level shifter design, we compared 3 main technologies: resistor-based, op-amp-based, and transistor-based. Resistor dividers are simple and cheap, but they're too slow and fragile for high-speed digital signals, and they mainly only work in one direction. Op-amp-based designs can shift voltages, but they're slower, power-hungry, and not really intended for fast digital interfaces. Transistor-based shifters, on the other hand, are much faster, more reliable, and support both unidirectional and bidirectional communication, making them the best choice for our application. From there, we looked at several level shifter ICs and ended up selecting the TXS0108E Power because it supports a wide voltage range from 1.2 volts to 5 volts, which is perfect for our 3.3 volt to 5 volt conversion. It also has a very low propagation delay at just 1 to 4 nanoseconds, ensuring reliable, high-speed communication between the FPGA and the LED matrix.
For our flash memory, we decided to use the 24LC16B flash memory, which is our onboard flash, due to the fact that it has a larger size than the other options available. The SPI protocol is easier to implement than parallel protocol and has smaller package size. And it also runs on quad SPI, not normal SPI, which means it has higher bandwidth than other SPI models. It also is available on board, which reduces the complexity of the implementation and helps overall implement the flash memory in our project.
When choosing an instruction set architecture for our project, we wanted to choose something that was flexible and easy to develop with. We chose about 3 different instruction set architectures, mainly being RISC-V, ARM, and x86. Now, RISC-V and ARM are both RISC type instruction sets, meaning they're not complicated. And the x86, which is the classic standard powerhouse that most of our PCs run, is a CISC, which is complicated. All of these instruction sets are quite capable, but we decided to go with the RISC-V architecture due to its open source nature, allowing us to flexibly control and design software. Specifically, we wanted to choose the RV32IM instruction set architecture, which only has integer and multiplication hardware support. This means that there's no floating points, making it more simple and easier to work with.
For the CPU core, we looked at 3 different RISC-V implementations taken from open source repositories in GitHub. The first option was an RV32IM core with a full 5-stage pipeline. It includes forwarding and hazard detection, but it's more complex than what SPUD really needs, and it hasn't been tested on FPGAs. The second option was a simpler RV32I implementation that could either run as a single cycle or multi-cycle processor. It's FPGA friendly and well tested, but it doesn't include multiplication or division support, which limits the kinds of programs that we could run. The last option was the ultra-embedded RV32IM core. This one was recommended to us by a fellow professor. It supports the RV32IM instruction set, includes optional caches and AXI bus support. It comes with strong documentation and has already been verified in SoC designs. Even though it's pretty complex, it seems like the most reliable source for SPUD, so that's why we picked it. We had several tool options that we could choose from for this project. Ultimately, we went with Vivado and the RISC-V GNU toolchain. Vivado handles synthesis, implementation, and simulation, while the toolchain compiles the C programs like the games into machine code for the CPU. We considered OpenOCD for debugging, but decided against it because it would add extra complexity without much benefit.
For our PCB design, we chose KiCad as our software. We compared it to other tools like Eagle and Altium, but KiCad stood out because it's open source, free to use, and still has the professional features we needed, like the PCB layout, 3D modeling, and built-in design rule checks. We designed a custom PCB that acts as a hat to sit directly on top of the FPGA. This hat allows us to add connectors that make secure connections to both the LED matrix and the arcade controller PCB. We also implemented 2 level shifters on this hat, which ensure that the signals are controlled at a safe voltage level. Finally, the button inputs from the arcade controller PCB are routed through the FPGA's GPIO pins, enabling real-time interaction with SPUD. This is the schematic for our main PCB. This connects the FPGA to the LED matrix and the arcade controller PCB. Since the FPGA runs on a 3.3 volt logic and the LED matrix requires 5 volts, we added 2 level shifters that we selected to handle that voltage difference. The board also distributes power to the matrix and uses capacitors to keep the signals clean and stable. The FPGA then sends timing signals and control signals through the headers, so the main PCB acts as a central hub between our hardware and the LED display. Here's the PCB layout for our basic two-level design of our peripheral interface HAT PCB. Here's the schematic for our arcade controller board. This handles all of the button inputs, and each button has a pull-up resistor, so the signal stays at a clean high level until the button is pressed. This design keeps the inputs simple but reliable. The controller PCB also connects back to the main board with a header, so it's easy to wire and keeps the button layout organized. The arcade controller PCB layout is also a simple two-layer design similar to our HAT PCB, with just one connector connecting back to the main PCB.
Software is critical to Project Spud. As you can already tell, we're making a CPU, so we're going to need some instructions to run on that CPU. Let's talk about some of the development tools that we've made for Project Spud. I'd like to introduce SpudKit, a bundle of tools and software that is built for code designed to be ran on Spud. Essentially, it's a C library which combines ARM scripts, linker scripts, and also build scripts. This allows us to quickly and easily develop code designed to run on our CPU. Now that we have our program, we need to load it into memory. We start at the C code, and then we compile it down into an ELF. Then we have a custom Python script which will turn the CPU into a debug mode, which will access the bridge, hold the CPU into reset, and then have direct access to the DDR memory, which is RAM, and it will load our program onto it.
Let's take a deep dive into the SPUD CPU. The best way to represent Verilog is in a hierarchical format. So here we have a few modules that we go into. So we have the top module, the very, very top, which is represented by the darker gray box. Then we have FPGA top and the DDR RAM that belong in the top. Then inside FPGA top, we have the debug bridge, the RISC-V SoC, and the AXI4 CDC, which represents the clock domain crossing for the AXI4 protocol. Inside the RISC-V SoC, we have a core taken from Ultra Embedded, and we have the SoC, which was partially taken from Ultra Embedded, but we're also making our own personal SPUD customizations in there. If we dive even deeper into the SoC, we'll see that there is an AXI Lite tap controller, which basically handles all the communication between the CPU and the peripherals. So we have all the peripherals that Ultra Embedded has created, but we have included 3 additional peripherals that we are designing the Verilog for. So that is the LED controller, the arcade controller, and the display controller. Inside the display controller, we have a display core, which handles all of the matrix mapping for the display. It uses GPIO to send those values out into the display. We also have the arcade controller, which has buttons that send the inputs from those buttons into the arcade controller peripheral and send that back to the CPU for processing. On the left-hand side, we have a map or a table of all of the peripherals, their base addresses, and some important information related to them.
Our LED matrix uses an interface called Hub75. It has 6 RGB pins, one for each panel. It has 2 panels, and it has 5 addressing pins, but each address corresponds to a row on both panels. So one address corresponds to 2 rows, one on the first panel and one on the second panel. And the clock progresses the shift register, so we don't have to manually send a signal to do that. All you have to do is send the clock signal and it moves on to the next bit in the shift register. So our software comprises of loops that iterate through the addresses and loops that iterate through each clock cycle to fill out the single bit of data. We do a 64 bits of data per row, and we move on to the next row by incrementing the address pin. After we do that for all rows, we finally enable the latch signal and we enable the output signal, and our image should be displayed.
For prototyping and testing on the hardware end, we did FPGA synthesis, place and route, and bitstream generation. We're also going to be doing button input testing for the arcade controller. we have been doing visual tests of the matrix display and the LED controller, and we will be doing a resource utilization check on the FPGA. For the software side, we have been simulating the CPU using Verilator, which is an open source simulator for Verilog. We've also been running compiled C test programs like booting Linux and printing Hello World just to make sure that everything looks good. Lastly, we've been integrating the testing of software with custom peripherals like the arcade controller and the display. If we look on the right at the top, that highest image represents the CPU core simulation testing. So this was a test bench provided to us, and we made sure that the CPU was working properly. So you can see the different tests like shift left, shift right. All these different tests seem to be going well. If we look at the waveform, this is for the Hello World simulation. You can see the different signals going, the addresses changing so that the program can run smoothly. And then at the bottom, we can see that the test for Hello World worked great.
We ran multiple tests to verify the integrity of our hardware. For example, we used oscilloscopes on pins to verify that we are receiving the expected voltage levels. We've received the expected frequencies. We received the expected pulses. We also designed test benches on Verilog to show when the CPU is in reset and when the debug bridge is enabled. This helped a lot. And we were able to successfully verify the implementation and synthesis via the Vivado simulations and test benches. And we finally were able to successfully load machine code to test out the RAM and verify that our UART works as expected and outputs the expected outputs. We encountered a lot of challenges for our project. One of these challenges was the unstable connections for our LED matrix caused by the breadboard and cables, which caused the shown visible glitches. Our simulator setup was difficult, which delayed our testing, displaying the values that we need to verify functionality. And overall, the project itself is difficult. The RISC-V design is very huge. It's all comprehensive, so there was many failure points that we had to account for. Our memory also was memory setup was difficult to implement to work with our DDR3 chip. Vivado was difficult to install. It was difficult to install the board files too. And building the custom build scripts to generate the machine code was also a difficult process, which also delayed us a little further.
The goal for the budget was to stay under $500. We were able to achieve that with a lot to spare, with the biggest costs in our budget being the FPGA and the arcade controller buttons.
Here is the work breakdown for our team. So Gabriel is working on the RDS7 expansion board PCB and all of the power management. He's also working on the user control interface PCB and the soldering and assembly. Mohammed is working on the matrix display interface, the bit shift display control logic, and the C library development for the display. Frank is our team lead and oversees all of the tasks. He's working on system integration, infrastructure setup, and the spud kit, which is our demo C library development. Lastly, I'm working on the SoC design customization, the RISC-V toolchain setup, and the CPU simulation and testing.
The end goal for this project is for each member to create their own unique interactable demo. As you can see here on the right, we've designed some software using SpudKit to render a 3D spinning donut. We have a few more ideas on what we'd like to show you on demo day. Interactive ones involve chess, Tetris, and maybe even Doom. But also, it'd be cool to show some simulation, like encoded video playback, sorting algorithms, and Conway's Game of Life.
Our current progress on the project is we have the PCB fully designed and we have it ready. We have the CPU fully implemented in the FPGA. We have some peripheral customization in the SoC, and we have a basic display program that verifies that our display works for now. What we need to do for our next steps is fully implement the display core, the driver, have full-fledged peripheral customization in the SoC, create high-level programs and program them on the CPU, do further testing and verification to ensure that our project works as intended, integrate the system PCB, all the connections, all the soldering, all the power components, and also do further system testing to ensure that our code is fully operational with minimal faults. For now, we have a rough estimate of 50% project completion, and we hope to achieve 100% soon.
Thank you very much for your time. This has been Project Spud.